Good morning, everyone. I'm Sudarshan Ambala, working as faculty in physics with the Government City College, Hyderabad, Telangana. Today's topic is address, half address and full address. Before we start with this topic, I just want to recap all the other digital principle topics we have covered up so far. We have studied the number system, uh, binary number system, decimal number system, octa number system, hexa number system. We have studied how to convert from one form to another. We have studied the Boolean algebra, all the arithmetic rules for addition, subtraction, multiplication, and division. Also, we did ones complement and twos complement, how we can do the subtraction using ones complement and twos complement. Then all the logic gates, the fundamental logic gates as AND, OR, and NOT. Then universal gates, NAND gate and NOR gate. Then some special gates we have covered up called XOR gate and XNOR gate. Then one theorem we did called De Morgan's theorem. The statement was like complement of sum of two inputs or more than two is equal to product of complement of two numbers. And second theorem was complement of product of two numbers or more inputs, we can say, was equal to sum of complement of two numbers. So after this, we are now switching over to an adder, which are of two types, half adder and full adder. Before this adder, again, I just want to recap as linear circuits and non-linear circuits. Basically, previous class you have seen how the transistor can be used as an amplifier. Input section and output section of the transistor should be always into forward bias and reverse bias respectively. And because of the input section forward bias nature, the current will be high, so impedance will be low. Whereas in the case of output section, it is into the reverse bias, or we can say that it is non-conducting stage. So it was almost the current was negligible. It means the impedance was high. So this input section low resistance was converted into output section high resistance. So basically we can say that the transistor can be used as an amplifier. So in the case of amplifier, where we use an input as a sinusoidal signal or any of the pulses. So for every change in the input circuit, the linear amplifier produces corresponding change into the output circuit. So this type of circuits we say as linear circuits. If you take an example, an application of a transistor as a switch, because it can be used as a switching circuit. So in that case, switch itself can be on and off. So the function of switching circuit is only to show the presence or absence of the output in accordance with the certain magnitude of input. So this operation we can say as a non-linear circuit, because the magnitude and waveform of output have no relation with the input. The switching circuit represents only what? Only on and off. So it doesn't, the output of the circuit will not depend on the magnitude and or the nature of the input. So these type of circuits, we can say it as a non-linear circuits. As we also covered the gates called logic gates. So that's nothing but circuits which are used to process digital signal can be called as a logic gates. So here in the case of logic gate, we can have one or more input voltages, but the output will be only one. And these gates we have studied saying that can be of two types. One is combinational logic gates and the other is called sequential logic gates. So what was that, the combinational as well as the sequential? In the case of, if you see, in the case of combinational gates, the output at any instant depends upon the inputs at that instant. But in the case of sequential gates, the output depends upon the order or sequence in which the inputs are applied. Like I can say that, the examples of combinational gates are OR gate, AND gate, NOT gate, NAND gate, NOR gate, XOR gate, and all these gates. So if you recollect the output of an OR gate, if you have a two inputs, the output was Y is equal to A plus B. In the sense, there are four possible combinations for the input section, like 0, 0, 0, 1, 1, 0, and 1, 1. So now here, as Y is equal to, output was equal to A plus B, if you give an input as 0 and 0, 0 plus 0 was 0. Then 0 and 1, the second input, 0 and 1, 0 plus 1 was 1. 1 and 0, the output is 1. So if you see the sequence of the order of the input, the OR gate, like even if it is a 0, 1 or 1 and 0, the output is only 1. So this can be called as a combination. Whereas the sequential gates, the example for sequential gates are flip-flops, counters, registers, because these are sequential gates. The output will depend on the sequence, the order or sequence in which the inputs are applied. So those gates are called as sequential gates. Now address. So what are address? Now let us see half adder and full adder with its truth table. Truth tables are nothing but the possible combinations of input, and appropriate output can be said as truth table. So an adder is a digital logic circuit in electronics that implements addition of numbers. In many computers and other type of processors, adders are used to calculate addresses, similar operations, and table indices in the arithmetic logic unit and also in other parts of the processors. These can be built for many numerical representation like XS3 or binary coded decimal. Now how the adders are classified? It are classified into two divisions. One can be called as in half adder, the other is full adder. So the half adder circuit has two inputs, A and B. It adds two inputs digits and generate a carry and sum. Whereas if you see the full adder circuit has three inputs, A, B, and C. It adds three input numbers and it generate a carry and sum. We'll see the difference very elaborately into the next slide. So these are the classification. This is how the schematic circuit diagram of half adder and full adder. You can see here, this is an, I'll just take this. Here we can see that this is an exclusively OR gate and this is an AND gate. And here we have used two half adders so that the output, final output will be called for the full adder. So three inputs like A, B and C input, and this is C out, carry out, this is carry in, and this is the sum. This is called sum and carry. So what is half adder and full adder? We can say that the logic circuit that adds two bits producing a sum and carry to be used in the next higher position can be called as a half adder. The half adder adds two binary digits called as augend and addend. Half adder produces two outputs, one is sum and the other is carry. XOR is applied to both inputs to produce sum. As you can see here, the circuit diagram. For the both inputs A and B, we have used an exclusively OR gate so that the output of the XOR will give as a sum of these two numbers. OR gate is applied to both inputs to produce a carry. Now, this is AND gate is applied to both inputs to produce a carry. Now you can see here. So here in the case of half adder, to get a carry we use an AND gate, whereas in the case of full adder we use an OR gate to get the carry out. Now the full adder adds three 1-bit numbers like A, B, C. Each one is nothing but 1 bit. So the full adder adds 3-bit numbers, or we can say that the difference, we can say that the half adder can be used for binary addition of lowermost bit only, because it cannot accept the carry in the from previous additions. So for this purpose, we need a 3-input adder, which is called as a full adder. So the full adder adds three 1-bit numbers, where 2 can be referred to as an operands, 1 can be referred to as a bit carried in. So two operands in the sense A and B, and the other one is bit carried in, can be called as an C in. It produces 2-bit output, and these can be referred to as an output, carry and sum. This is called as an input carry and this is called as an output carry. Half adder. Using half adder, you can design simple addition with the help of logic gates. So for an example, addition of single bits if you have taken. So single bits in the sense we will have 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. So what is happening according to the Boolean algebra? We can say that the rules set by the rules are like 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1, 1 plus 0 is 1, and the last one, 1 plus 1 is 0 with carry 1. So here we have a carry which can be given to the next higher column for the further addition. So earlier we have studied as per the rules, Boolean arithmetic rules, we said that 1 plus 1 is 1. Basically 1 means high. So if you give an input as in 2 inputs in high and high, the output was high. When you do a mathematics addition for the single bits, 1 plus 1 is 1, or we can say that 1 plus 1 is 0 with carry 1. So this is for the basic addition for the single bits. Or these are the least possible single bit combinations because it is the lowest. But the results for the 1 plus 1, this is what the problem is. But the results for 1 plus 1 is 1, 0. The sum results must be rewritten as 2-bit output. Because here if you see the previous slide, we have taken a single bit output. 0, 1 and 1. But for the 1 plus 1, we need 2-bit output because the output is 0 with carry 1, or we can write it as in 1 0. Because 1 0 is a binary equivalent of decimal number 2. If I take 1 and 1 into the form of decimal, so binary is 1 equivalent is decimal 2. So 1 plus 1 is 2. And if we see this 2 as a decimal number, 2's binary equivalent is 1 0. So the results for 1 plus 1 is 1 0. The sum results must be rewritten as 2-bit output. So thus the equation can be written as, now we have wrote the same thing into the 2-bit output. So we are saying that 0 plus 0 is equal to 0 0, 0 plus 1 is equal to 0 1, 1 plus 0 is equal to 0 1, and 1 plus 1 is equal to 1 0. It means 0 with carry 1. So the output of 1 0 is carry out, because these are 2-bit numbers. So this 1 is carry out. Sum is the normal output and carry is the carry out. So we can say that the sum here is 0 and this 1 is carry out. This is a block diagram for an half adder. So we have two inputs as we discussed earlier. This is A input and B input, and we have two outputs. Unlike in the case of logic gates, AND, OR, NAND, NOR, or NOT, there we have seen no matter how many inputs we give, the output was 1. But whereas in the case of half adder and full adder, in the case of half adder, 2 inputs are there and 2 outputs are there. In the case of full adder, 3 inputs are there and 2 outputs are there. So this is one input as an A bit and the other bit is B input. Output is sum and carry. So we normally write sum as a capital S and carry as a C. This is the truth table for the half adder. So for all the possible combinations, for 2 input will be 2 to the power of n. So 2, because the radix or the base of binary is 2. So 2 to the power of 2 will be 4. So here the combinations are 0 0, 0 1, 1 0 and 1. So what's happening? If I take the input as in 0 and 0, sum will be 0 and carry will be 0. 0 and 1. So 0 plus 1 is 1. 1 is sum, whereas carry is 0. 1 plus 0, sum is 1 and carry is 0. Whereas if you see the inputs for the 2 as high, like 1 and 1, here the sum will be 0, whereas the carry is 1. So we can say 1-bit adder can be easily implemented with the help of XOR gate for the output sum and AND gate for the carry. If you see the previous diagram, if you see this one, a schematic here, the output of sum is taken as an output of XOR gate, whereas the output of AND gate is considered as a carry. So this is sum and the other is carry. When we need to add two 8-bit bytes together, it can be done with the help of full added logic. The half adder is useful when you want to add 1-bit digit quantities only. A way to develop a 2 binary digit address would be to make a truth table and reduce it. When you want to make a 3 binary digit adder, do it again. We need to repeat it again. When you decide to make a 4-digit adder, again you have to repeat the same steps. The circuits would be fast, but the development time is slow. So these are few of the drawbacks for the half adder. This is the circuit we explained very clearly. XOR gate and the AND gate. Output of XOR gate is sum and output of carry is output of AND gate is carry. The simplest expression uses the exclusively OR function as this is sum. Sum is nothing but A mod 2 addition of B, and carry is nothing but A dot B. So an equivalent expression in terms of basic AND OR and NOT gate is sum. It can be like, you know, A dot B, it is mod of this, and then plus A dot B. B is nothing but it's a complement. So these are the other expression of expressing the sum with this particular equation. And this is VHDL coding for half adder. It's nothing but very high speed. This is a very high speed integrated circuit hardware description language. Normally this language in electronic design is used for automation of electronic design automation to describe digital and mixed signal systems such as field programmable gate arrays and ICs, integrated circuits. So this is how the coding is done for the half adder to get a truth table as what we have discussed. So two inputs and the output, and what is the condition if it is less than or equal to A, then the XOR gate output should be coming here, and if it is less than or equal to A, then the AND output is coming. So this is how the VHDL code are written for the truth table, or to get the truth table for half adder. Let us understand full adder. Full adder is difficult to implement than a half adder. The difference between half adder and full adder is that the full adder has 3 inputs and 2 outputs, whereas half adder has only 2 inputs and 2 outputs. The first 2 inputs are A and B, and the third input is an input carry as C in. When a full adder logic is designed, you string each of them together to create a byte-wide adder and cascade the carry bit from one adder to the next. This is how the block diagram of full adder can be written. So A and B are inputs. The third is carry in, and there are 2 outputs. One is sum, the other is called carry out. The output carry is designated as C out, and the normal output is designated as sum. You can see from here, this is carry out and this is sum. The full adder logic can be implemented with the truth table. The output S is an XOR between the inputs A and the half adder, sum output with B, and C in inputs. Take C out will only be true if any of the 2 inputs out of the 3 are high. This is with the condition only the C out will be high. This is the truth table for the full adder. 3 inputs, so 2 to the power of 3. The possible combinations for the input will be 8. And output, you have sum and C out. So let's go by each conditions. When you have 0, 0 and 0, the sum will be 0 here and the C out will be 0. If you take the second condition 0, 0, 1, sum will be 1 and C out will be 0. Similarly 0, 1, 0, sum is 1 and C out is 0. So here we can say that this is a combination gate because we have changed the sequence of the input like 0, 0, 1, the output is 1 and 0. Again, we have changed the sequence saying that 0, 1, 0, but the output is same like 1 and 0. So these are called, or it is an example of combination gates. The next input is 0, 1, 1. The output is 1 plus 1 is nothing but the sum will be 0 and the carry is 1. Here again 1 0 0, so 1 plus 0 plus 0, the sum will be 1 and carry is 1. 1 plus 0 plus 1 will be, sum will be 0 and carry is 1. 1 1 1, it means 1 plus 0 will be, sum will be 0 and carry is 1. And if you take all the three inputs as an high, 1 1 1, then the sum will be 1 and the carry will be 1. So we will get both the output high, sum as well as carry out, only when all the inputs to the full adder are high. So we can implement a full adder circuit with the help of two half adder circuits. We'll see the next circuit with a block diagram using two half adders. First half adder will be used to add A and B to produce a partial sum. Second half adder logic can be used to add C in to the sum produced by the first half adder to get the final S output. I'll explain once again. If any of the half adder logic produces a carry, there will be an output carry. A C out will be an OR function of the half adder carry outputs. The implementation of larger logic diagrams is possible with full adder logic. A simpler schematic representation of one bit full adder is, this is how it looks. So we were saying that, using two half adders we can have a full adder. So here we have used two XOR gates. So to this particular XOR gate, directly we have given as in two inputs A and B, and this partial sum, the output of this particular XOR gate is nothing but a partial sum. So that partial sum is given as an input to the another XOR gate, and this is the third input given to the XOR gate. So we were saying that we can implement a full adder circuit with the help of two half adders. First half adder will be used to add A and B to produce a partial sum. This is the partial sum. A second half adder logic can be used to add, this is C in, to the sum produced by the first adder to get the final S output. So this is how we were saying that A and B are the inputs for the XOR gate, will get the partial output, and this is the third input given to the second XOR gate. So this is partial output of the XOR gate as in partial sum, and this is C, and this we can say that this is a final output. And how the input to this NAND gates are given, this A and B are directly given to one of the input, to input as in one of the AND gate, and here the partial sum we say the XOR first XOR gate's output, and the C in, see you can see that this is the C in, this is short. So this is the partial sum is one of the input and C in is the another input. So these two inputs are given to the third, to the second AND gate, and the output of these two AND gates are given as an input to the OR gate, and whatever the output we have collected to the OR gate is nothing but C out. So this is a schematic representation of a one bit full adder. So here you can see that this is two inputs P and Q. The output is sum and here is carry. So this sum is an input to this half adder, and this carry in is the third input to this half adder, and this C out is as an input to the OR gate, and this C out is given to the input to the OR gate, and this will be the carry out, okay, and this will be the sum. So we can say that this is P and Q half adder, this is carry in and sum. For this half adder P and Q, and the output is carry in, and this should be carry in, and this is sum. So this can be say that full adder design using a half adder. With this type of symbol, we can add two bits together. So this is how we can add two bits together. Taking a carry from next to lower order of magnitude and sending a carry to the next higher order of magnitude. In a computer, for a multi-bit operation, the usage of full adders, each bit must be represented by a full adder and must be added simultaneously. To add 8-bit numbers, you will need 8 full adders, which can be formed by cascading 2 of the 4-bit blocks. Combinational circuit combines the different gates in the circuit. Example are encoder, decoder, multiplexer, and demultiplexer. So the characteristics of combinational circuits are as follows. The output at any instant of time depends only the levels present at the input terminals, not the sequence. It does not use any memory. The previous state of input does not have any effect on the present state of the circuit. It can have a number of inputs and a number of outputs. The relation is between the full adder and the half adders are half adder produces results and full adder uses half adder to produce some other result. Similarly, the full adder is of 2 half adders. The full adder is the actual block that we use to create a arithmetic circuit. So whenever you use any digital electronics for the calculations, then the full adders are used. This is again the VHDL code, nothing but very high speed integrated circuit hardware description language, basically used in electronic design automation to describe digital and mixed signal systems, uh, such as field programmable gate arrays and ICs also, integrated circuits. So this is the coding for that. So with this, we covered up almost all the digital principles, right from the number system, conversion, arithmetics, gates, then Boolean algebra, universal gates, De Morgan's theorem, and half address and full address. So thank you one and all. Thank you for having patience to go through all the videos. Thanks once again.